The Hayabusa2 is a Japanese space probe designed and built for asteroid sample return. The space probe visited the asteroid Ryugu in June 2018 and successfully returned surface samples to Earth in December 2020. The Hayabusa2 also carried 3 rovers, which it deployed to the surface of Ryugu. The Hayabusa2 Optical Navigation Camera System, ONC, contains 2 wide angles and a telescopic camera. The Minerva-II-2 rover, for which we are particularly interested in for this paper, was mounted near the ONC W2 camera. The rover was deployed from the Hayabusa2 in October 2018 to perform gravitational measurements. The Hayabusa2 then moved to an observation altitude to observe the orbital propagation of the rover over the next few days. Shown at the top are example images of the rover taken by the telescopic camera. From these measurements, the team at JAXA were then able to back-propagate the rover's orbit about Ryugu. Additionally, the team at JAXA were able to precisely estimate the initial deployment velocity of the rover. This study is a great example of deep space missions and their challenges. The JAXA team worked with limited data by employing a number of simulations and relatively complex analysis to determine the rover's deployment velocity. In this paper, we independently perform a similar analysis using computer vision techniques. The Minerva-II-2 rover is a highly symmetric, regular octagonal prism, as depicted here. Here are images of the rover deployment taken by the ONC wide-angle 2 camera at 3-second intervals. We constructed a geometric model in SolidWorks and rendered images using a single directional light source. We then focused on modifying the renders to replicate the characteristic noise artifacts of the real images. The final dataset contained 10,000 images, with all noise artifacts included to varying degrees. Finally, we addressed the topic of interest, spacecraft pose estimation. As seen in this real example image, we were able to reliably estimate the axis of symmetry, shown here in blue. However, due to the symmetry of the rover, our pose estimation for each image could only be constrained to 16 possible poses. Because we had access to geometry data, we employed a landmark pose estimation pipeline depicted here. The CNN landmark detector was trained on the 10,000 image dataset discussed previously. An input image was cropped, and the CNN detected the landmarks. Again, due to the symmetry of the rover, we were unable to train a CNN to uniquely identify landmarks. Instead, we trained the network to identify 16 vertices. We then recovered the possible poses from these vertices using P3P, bundle adjustment algorithms, and iterative error reduction. Here we show a simulated tumbling motion of a non-symmetric octagonal prism. The pose is uniquely identifiable for each image, and the process is relatively straightforward. Finally, we see the results on the real Minerva-II-2 images. The axis of symmetry is uniquely identifiable for each image. Additionally, with our calculated location data, we were able to validate JAXA's deployment velocity estimation using a completely independent set of images.